Hello, my name is Denis Pasero, product manager at Ilika. We are a UK-based company based in Southampton in the south of the country. Thank you for the invitation to talk at this event. I'm going to be talking to you about how solid-state batteries may enable product design in medtech. We've been working on solid-state material and processes for over 10 years in our Stereax program, and this resulted in a range of micro batteries at the milliwatt hour level, which we are deploying in next generation medtech devices, but also industrial IoT sensors. We have a second solid-state battery program, the Goliath program. These are much bigger batteries at the watt-hour level for EVs and consumer electronic. So that's a different thing. I'm going to be concentrating on Stereax today. And what we see when we talk to product designers, startups in Israel, in the US, all over the world, is a shift from current generation and conventional technology of implantable devices, from devices that are quite bulky with rather large batteries, yes, with quite a lot of capacity in them, but rather thick. And these use conventional lithium-ion or other type of chemistries, but a liquid electrolyte-based chemistries, let's say in a metal package. So the disruptive product design comes first from the possibility of miniaturizing electronics and PCBs and devices in general, and also the availability of ultra-low power electronics. So miniaturizing those devices enables the implanted devices to be placed nearer to the organs that they intend to target: the eye, the lungs, the heart, inside arteries. Okay. It also enables insertion in the body in a simpler way. No need for several days of operation and recovery in an hospital. This could be done in a few hours or half a day at your medical practitioner. But those new devices require a new conversation. They are smaller, they'll have less energy in themselves. So it's about understanding whether the patient will be happy to recharge the device more frequently, maybe every week, maybe every days or few days. And of course, some designers are also interested in learning how we can harvest energy from the body to recharge the devices. So this product design is creating a new type of next generation devices within neuromodulation, from vagus nerve stimulation to sleep apnea to spinal cord stimulation or deep brain. Many different types of implanted sensors, pressure, oxygen, temperature sensors, pulmonary sensors, some much smaller so-called leadless pacemakers inside or just outside the heart, and needing backup batteries for this. And of course, the well-promoted smart contact lenses. So these are all applications, next generation applications that need special batteries, and they are an ideal fit for solid-state batteries, SSB, because they need extra small components, no need for such a high capacity, and they sometimes need unusual shapes, and still very long cycle life and shelf life, whilst also, of course, needing a safe technology. Okay, so what is a solid-state battery? Well, actually, it is a lithium-ion battery made in a different way with different materials. There is no liquid or polymer electrolyte in them. It's all solid ceramic materials. So it is safer. It won't leak out and won't create damage or a possible explosion. They are fabricating using equipment that is familiar and very common in the semiconductor and MEMS industry, evaporators, sputters. And you can see here on the screen, on the right here, a 6-inch wafer with many of our cells on them. The cells are patterned using masks and photolithography and etching and other microfabrication techniques. So we can change the size, we can customize the size and the shape and make them really quite small. So in terms of technical electrical advantages, they have predictable long cycle life, and the graph in the middle shows that even after 1,000 cycles at 5C discharge rate, we not even reach 90% of the initial capacity in some of our batteries. They have high charging and discharge rates, C rates. Standard is 1C, but we can go to 10 and even 20C in pulses. I'll give you more electrical data later, and it can be charged rather fast. And in order to increase energy, they can be stacked. So we are indeed first enabling miniaturization, going from large devices, as you see on the left-hand side, to devices that are really at the millimeter scale. A device like this would have the advantage that it could be inserted, for example, through a catheter with a very narrow gauge inside the body or an artery, rather than going through a complicated operation. We are enabling new applications like the smart contact lens, which has no other solution than a solution like a miniature solid-state battery to power their electronics. And in general, we're just enabling future applications within, again, neurostimulation or implanted sensor, enabling miniaturization whilst keeping good energy densities. Okay, so I'm going to be concentrating now on how you may be able to design in a solid-state battery in your disruptive medical device. Concentrating first on size and form. We can make various sizes and I've explained shapes also, from the centimeter squared batteries, you can see on the top left, to very, a few millimeter by a few millimeter in terms of footprint, and everything in between. Again, we can make customizable shapes from things that are long and thin and narrow to little cubes of stacked cells on top of each other and interconnected in parallel, to unusual shapes like this trapezoidal shape. Here you can connect them next to each other to form some rings, circular shapes, or this double pyramid shape. Again, that's the idea of a battery that would fit efficiently within a tube or a catheter. They can also be made quite thin, in fact, very thin. When they are deposited, that's the picture in the middle, they are depositing on a thick substrate of glass or silicon. And the battery in red is actually quite small. But thankfully, there are some very common techniques for thinning substrate. And you can get now, we can make cells that are 150 micrometers in thickness. And we're exploring going even thinner, below 100 micrometers. The second consideration you will likely have is, how can such a small battery provide enough energy and power for my device for enabling communications or sensing or stimulation? What we do is, again, stack those cells on top of each other. You have a little cross-section photograph on the top right here of 6 cells connected to each other in parallel to increase capacity. And you can see it is still less than 1 millimeter thick. We also increase the cathode thickness, which is the lithium reservoir, in order to provide enough current for pulses. So this table down at the bottom of the slide is a shortcut to our roadmap. You can see that we are, by increasing cathode thickness and decreasing the substrate thickness, aiming for an increase in energy density, and also an increase in maximum continuous and maximum pulse current, which is typically about 20C. And you can see that we can already provide a few milliamp going towards double-digit milliamp of pulse current, because typically the application is not really a continuous current application. You will have an energy profile which resembles peaks and pulses. How do you package and handle and mount these batteries? Our vision is that solid-state batteries do not resemble a battery anymore. The battery is not an add-on to the rest of your electronics. It can be considered like another integrated component, another IC, and handled in the same way as other ICs. We can connect, and you could connect those batteries using a conductive epoxy, room temperature. wire bonding, and we are exploring laser welding and other conductive film and printing techniques. Because those batteries do not have a liquid electrolyte that may leak out, they need a minimum packaging. In fact, you could just use them as bare dies, and you've seen several pictures of those batteries already. They are bare dies, but they could also be provided in an hermetic sealed package. But here, there's a loss in energy density. But it is good to know that in an hermetic package, the cycle life could be improved. Okay, so like other batteries, solid-state batteries will need care in terms of care and protection. So they need care in terms of avoiding over and under voltages. And you need some components to allow conversion from the 3 to 4 volt voltage window of those batteries to what is useful for you. Now, thankfully, there are already ultra-low power PMIC, power management ICs, available off the shelf, and at least some of them. And they have very efficient way of converting the voltage to what is useful for you. Whilst other designers prefer to go through the ASIC route and design their own ASIC with similar functionalities to the PMIC above. We recommend the Swiss company Microdoule, who has very efficient and appropriate ultra-low power ASIC capabilities. Those batteries being inside the body, typically for implants, but also, out of the body, small devices, can be recharged using wireless technologies from electromagnetic coupling, induction techniques, RF, ultrasound also. We've demonstrated that they can be charged in that way. And also, they can be charged using harvested energy from the body. They have very low leakage current, which means that energy coming from an harvester, which may be intermittent and ultra-low power, is stored efficiently thanks to the very low electric leakage. Importantly, as you charge a battery, especially a battery like ours, which can be charged fast, is that it does not heat up inside the body. It could be uncomfortable and even dangerous, if not within the standard legal limits. This depends on the charging rate and the size of the battery, but we can already say that they will not heat up more than a few degrees. Okay, so for an implantable, long life of operation is very important, of course. You don't want to remove the device because the battery has died because of cost and health complications and infection and possibly death. Depending on the device, the requirements go from 5 years, at the minimum, more typically 10 years, but it's clearly a move for more than that, 15 years also. Again, this is a conversation with the patient. Will they accept for those 10 plus years to recharge the battery very regularly, perhaps every day? Regardless, it needs a battery that can cycle for many thousands of batteries. So if you are thinking about what the exact battery needs to be in your device, come and talk to us. We have specialist engineers that can help you size the battery in terms of the energy density that you require versus its cycle life. We have many charts and graphs and calculators that can help you out. One of them is, for example, understanding that if the battery is discharged partially, so it's a partial depth of discharge, the cycle life will increase. So you may want to size the battery in that way. Okay, early next year, we will be launching a prototype 6-stack battery, which we call the Stereax M300. In fact, there will be a single cell version, if that's of interest. We will make this available for evaluation. So please contact us through the usual channels, emails, and our website. Of course, we have a booth here today. with my colleagues John Tinson and Avi Pincus, available to talk to you today. A few specs here. The stacked M300 will be less than 1 millimeter thick. Its dimensions is 5.6 by 3.6. Now, this is a standard size that we make available to you for evaluation. But remember, we can customize things for you. Maybe interestingly, you can see in the peak current section here that we start being able to provide some milliamp here, 6 milliamp of current. So this could be useful. So again, come and talk to us. We can work with you in several different ways. You could evaluate some of our standard products. So the M300 could be the next one that would be of interest for you. May not be exactly the right size, but get you used to working with this novel technology. You might decide then that actually I would like different dimensions and different electrical specs. We can customize the batteries for you. And we can provide at a later stage. You might want to start thinking, okay, for my FDA testing, animal testing, I might require some hundreds of batteries, maybe moving towards the thousands. We can provide that for you. And we also can go all the way with you for large volume manufacturing, whatever volume it is that is relevant to you. We are currently selecting fabs that will allow us to move from our pilot level for evaluation, pilot line level, towards high-level manufacturing. There's still about, let's say, about 18 months of scaling up, getting the fabs ready for high volume. But 18 months, typically, we'll find that is sufficient on your roadmap, considering you will have FDA testing and so forth, and prototyping along the way. Okay, so it was a pleasure talking to you about how we may be able to enable your disruptive technology to exist and how we could power it with miniature solid-state batteries. Again, we can answer all of your questions if you come and see us at the booth, and you can talk to me or my colleagues, or you could contact us through those contact details. Thank you very much for listening.